Hello. We now focus on another very important aspect of definite integrals, and that is certain fundamental properties of definite integrals, and these properties are very useful in evaluating definite integrals, which would otherwise take, without the application of these properties, those evaluations will take time and they would become very cumbersome. Sometimes it will be difficult to solve them also. So with that in mind, we are going to set up a few properties, state the properties and comment one by one as and when necessary. Now, we've titled the lecture as Properties of Definite Integrals. The first property that we have is, we write it down, we number it. The first property is integral a to b fx dx is the integral a to b fz dz is equal to integral a to b f lambda d lambda. In other words, when we are integrating and creating a definite integral, we are trying to find the value of a definite integral that is independent of the variable of integration used. In other words, the variable of integration is therefore called a dummy variable. Now, these are being given without proof. The proofs are very simple, but it's important to remember the bottom lines, and I'm writing it down. The bottom line, a definite integral does not depend on the dummy variable of integration. We use this word dummy variable of integration. This is very significant. So, in fact, here we also get one more answer. If it does not depend on the variable of integration, what does a definite integral depend on? The answer is 2. A definite integral can be dependent on the limits and can also depend on any parameter of integration which is independent of this. For example, if we have e to the power of lambda z, then the result could be a function of lambda, will be a function of lambda in fact. Okay. So, this is to be very clearly kept in mind, because when we do later on Laplace transforms and other definite integrals, we find sometimes difficult to comprehend that the definite integral just depends on the limits and any parameter which is independent of the variable of integration. In Laplace transforms, we know that we have a parameter called S. So, it can depend on S. In fact, Laplace transforms are S dependent. That we will see when we take courses in circuit theory or other such like courses. The next property which we put up on board is as follows. We will call it property 2. If we swap the position of the limits, then the value of the definite integral changes only in sign. In other words, if we have, for example, if we have a to b, this is the second property, we put a serial 2, fx dx is the minus of negative of b to a fx dx. In other words, swapping the limits, the position of the limits changes the sign of the definite integral. So, if we have one value from 1 to 2 as 5. If we integrate from 2 to 1, it will be minus 5. So just change the sign of the integral. The third one is if an integral, if a function is integrable in a limit in an interval from a to b, then it says that integral a to b f dx is integral a to c f dx plus integral c to b f dx. Of course, all these f's stand for fx. In other words, if we are integrating from an interval a to b, we can choose any point in between a to b, call it c. In other words, c lies between a and c is more than a and less than b. C is any intermediary point. So if the function is integrable from a to b, it is the sum of the integrations from a to c and then from c to b. So this c can be chosen in a convenient manner, as we will see when we are doing problems. That property is for 0 to a fx dx is equal to 0 to a f a minus x dx with no conditions imposed. This is a very unconditional property, and as I have said, this is probably one of the most frequently used properties to evaluate definite integrals, which look seemingly difficult and weird. We will take an example of this a little later, so that the next one is when we can put a number 5 and write down the property. Property says that when fx is a periodic function, if fx is periodic, with a period of a. In other words, f of x plus a is equal to f of x. So this is the period of the function fx. Then the property says integral 0 to n a fx dx is n times integral 0 to a fx dx. In other words, stated in terms of words, it is if I integrate a function fx which is known to be periodic with a period of a for n periods, 0 to n periods, the result is the same as n times an integration for one period. That is how it should be interpreted. It's very simple to interpret. I again repeat that if a function is periodic with period a, then integrating from 0 to n periods is the same as n times the integral from 0 to one single period. So that is property 5. This is also sometimes useful. The problem solving skills emerge when we are able to recognize which particular property to apply in a very particular case. That is where the crux of the whole problems lie. Which property to apply and which property will make the evaluation convenient. The next one is, if a function f is such that it is known that f of 2a minus x is f of x, then zero to 2a fx dx is 2 times 0 to a fx dx. Now here it must be very clearly understood that the property given here under this condition itself is just a sufficient condition. In other words, it is not necessary, it is a sufficient condition. There are many cases in which 0 to 2a will be twice of 0 to a, where this condition is not satisfied to start with. But if this condition is known to be satisfied for a particular function fx, then that condition is good enough to make this assertion that 0 to 2a fx dx is twice of 0 to a fx dx. Now, with that we wait for a while, and before we stop this lecture we are going to take up one small problem to illustrate how one might look at an integral that is complicated, and yet by the application of these properties, one or more of them, it can be made very simple. We will take a very simple example. It is simple after we use the properties. Now, as promised, I have put up one integral which is weird looking, it looks weird. There are cosines and sines, there is a limit from 0 to pi by 2, and there are square roots. Now, if we look at this integral, even without the limits, by itself, is something that we will say, no, let us not try this. Even with the limits, the situation is not any better if we do not know how to apply the properties. But let us see how we can simplify it. We have stated one property, that integral fx dx 0 to a is nothing but integral 0 to a f of a minus x. And while stating this, we have made a remark that this is probably one of the most frequently used of all the formulae. We will apply this. So, this is going to be, by that property, integral 0 to a, here a is pi by 2, under root cos pi by 2 minus x divided by cos pi by 2 minus x under root plus under root sine pi by 2 minus x dx. So, if we call this I, then I is also equal to, and this is nothing but 0 to pi by 2 root sin x divided by root sin x plus root cos x. So, if we reckon that I is root cos x over denominator, and the same I is root sin x over the same denominator, we can add the two integrals on the right hand side and write that we now have 2I as 0 to pi by 2 When we add this and this, the numerators become the same as the denominators. So we get 1 dx, and that is nothing but pi by 2. This leads us to conclude that I itself is nothing but pi by 4. So the beauty is that in evaluating this integral, we have not done any integration at all. That is the beauty of using the properties. I repeat once again that a weird looking integral which we started with does not need any integration from start to finish to get its value. It's just like a mango falling from a tree, and we have the mango in our hands. The value is I is equal to pi by 4.